Welcome to the Crazy Hat Chemist. So today we're going to do another video, number 23 in Electrons and Atoms. Bam! So today we're going to be talking about the Pauli Exclusion principle, and we're going to apply this to an atom, and we're going to apply this to helium. So again, I want you to pull out your periodic table, take a look at your periodic table, find helium. That's atomic number, or Z, of 2. Okay, so write out the standard nuclear notation for helium first. That's what I want you to first do. Okay, so we're going to come up with the definition of the Pauli exclusion principle, and then we're going to apply that and see how that fits into electron configurations and specifically an orbital box notation. So, for multi-electron atoms, i.e. anything greater than hydrogen, no two electrons can have the same set of 4 quantum numbers. That is the same NL, M sub L, and M sub S values. Okay, so that's why we're going to take a look at helium, because helium is the first element of which this can be applied to. Okay, so what you wanted to do is write out the standard nuclear notation for helium. Okay, and that is right there. That's 4-2 and the HE, or 4HE and the 2. Okay, that Z of 2 tells you how many protons are on helium. That is 2. And then how many electrons are in helium. That would also be 2. Because we're talking about a neutral element, okay, and something that is in the ground state, just like we started with these problems to begin with. So we're going to write out the electron configuration for helium, and that is 1s2. That is not read as 1s squared, it is read as 1s2. Okay, so just like before, that 1, what does the 1 mean? The 1 is the n value, the principal quantum number, because it is in energy level 1. That is, it's in the first period. Okay, the S is actually referring to the L value of 0, which is the angular momentum quantum number, and in this case, L of 0 corresponds to an S-type orbital, therefore the letter S. Okay, and so possibilities for writing out orbital boxes for this are the following. So the electron configuration, again, is read as 1s2. Okay, how many electrons can we fit in an orbital? A maximum of 2. So we're only actually going to be writing one single box here. And so that's why we have a single box. Okay, so here is the first electron, and this right here is the electron, the orbital box diagram for hydrogen. Remember, we have a single box, we have the 1s labeling of that box, that's the energy level and the type of orbital, that's the 1s, and there's a single upwards electron, that is the orbital box diagram for hydrogen. However, we're working with the orbital box diagram for helium, so we're going to have to add another electron here. So one of the possibilities, excuse me, is pairing up this electron with the same kind of spin. So what we're going to do is I'm going to show you if this is correct or incorrect by writing out the set of 4 quantum numbers for each of the electrons. So this first electron has the set of quantum numbers as follows. The N is 1, that corresponds to the blue number. The L is 0, corresponding to the S-type orbital. The M sub L is plus or minus all the L values, plus or minus 0 is 0. And the M sub S value is plus 1/2 because it is an upwards facing arrow. So now we're going to have the set of 4 quantum numbers, excuse me, for the second electron in this box. Notice that the N value is 1, the L value is 0 because it's an S-type orbital, plus or minus all the L values is still 0, that's why the M sub L value is 0. And then since this arrow is upward facing, it's also plus 1/2. So the rule here is that no 2 electrons can have the same set of 4 quantum numbers, and so this is a violation of that rule because the 4th quantum number of M sub S is the same for both of these. So this is not the proper way to write the orbital box diagram for helium. Let's give another try. That's another possibility. So I've got my orbital box. I've got my electron written as an arrow. Now this time I've gone outside of convention, but I want to do this just to show you really how it's done and how this Pauli exclusion principle is applied. I have the labeling of this box, and that is a 1s box. Okay, and if I pair this up with the same spin electron, now I'm going to write the set of 4 quantum numbers that represent each of these electrons. First, the electron on the left. That is an n of 1. That corresponds to the blue number of n of 1. That's the principal quantum number. The L of 0 is corresponding to the type of orbital. That is an s-type orbital. The m sub L value is plus or minus all the L values. The L values are 0, so plus or minus 0 is also still a 0. Since that is a downward facing arrow, that is down, then that is going to be a negative 1/2. Okay, let's look at that second electron in that box, and that is a n of 1. That corresponds to the blue number of 1. L of 0 corresponds to the type of orbital, s-type. M sub L plus or minus all the L values, that's also a 0. And since this electron is the same downward facing, that's a negative 1/2. Now, is this okay? The answer is no. This is also a violation of the Pauli exclusion principle. That is, no 2 electrons can have the same set of 4 quantum numbers. Okay, the m sub s value is the same in both of these examples, and that's why it's a violation. All right, so now let's go on to the next one. So I've got my orbital box, that is my orbital, and then I have my first arrow as we properly write it, which is an upwards facing arrow, unlike the second example that I gave. So this box is labeled. This is actually the orbital box diagram for hydrogen, like we did in the previous lesson. So make sure that you know that. However, we are doing for helium, so we need to add in that other electron. Okay, now adding in that other electron, we're going to have it of an opposite spin. So now what we're going to do is write out the 4 quantum numbers for each of these electrons. So that first electron that is an upward facing electron is n of 1. That n of 1 corresponds to the blue number, which is the principal quantum number. The L of 0 corresponds to the type of orbital. So L of 0 is an s-type orbital. M sub L is plus or minus all the L values, so plus or minus 0 would still be 0. And since this is an upwards facing electron, that's an orange electron upwards facing, that's a positive 1/2. Okay, so make sure that you note that. Positive 1/2, that's a clockwise spin of that electron. Now we're going to do the set of 4 quantum numbers to represent the second electron within this particular orbital. So n of 1, again corresponding to the principal quantum number, okay? L of 0 corresponding to the type of orbital, that's an s-type. M sub L corresponding to the orientation along the axis, and you cannot orient a sphere, and that's why the M sub L value is actually 0. Okay, but it is plus or minus all the L values, which plus or minus 0 is, of course, 0, because there are no positive or negative zeros. And now the m sub s value, notice it's a downward facing arrow, and it's going to be negative 1/2. This m sub s negative 1/2 is now a set, this corresponds to a different set of quantum numbers for each of the electrons within this orbital. So referencing back that rule of the Pauli exclusion principle, no 2 electrons can have the same set of 4 quantum numbers, and this is not a violation in it. Even though there are 3 quantum numbers that are the same, there's one that differentiates them, absolutely, and that is the electron spin in this case. Now, the m sub s as up, so here's my reference on this. If m sub s, if that arrow is going up, that means that you're going to heaven, and that's positive. Therefore, the positive 1/2. Generally, people view that going to heaven is a positive thing. Look at the arrow that is facing down. That arrow that is facing down is going to hell, and that's generally viewed as negative. That's why it's a negative 1/2. Hopefully that reminds you to put the positive and the negative in front of the m sub s value. You must have the positive and negative in front of the m sub s value, otherwise it doesn't work. Okay? Hopefully that worked well for you. Hopefully that describes the Pauli exclusion principle for you, and you can understand why the other 2 concepts here, other 2 orbital box diagrams, are a violation of the Pauli exclusion principle. Okay, that is another video. Here is another hat. This is coming from the same hat company in Spain that my wife and I travel to. And this is my summertime hat, not my wintertime hat. Okay, I look forward to more videos here, more chemistry. Give me a thumbs up on that video. Subscribe to my YouTube channel, and I will see you next time for more chemistry because I can't wait. Bye now.